We'll proceed on directional derivative along a vector u. So this is what we have been discussing. Directional derivative along vector u. If I have a graph function f, if I have a graph function f, then what is its derivative? Differentiation in calculus, derivative. What is its derivative along any vector u? What we know, if I have a graph if I have a function of a graph and function is single independent variable fx, then there is one possible derivative, that is dfx by dx. If fx is multivariable, where independent variable are two, x and y, if f is multivariable, independent variable are x and y, then what we are trying to do is we will calculate partial derivative along two axes, x-axis, y, df by dx, df by dy, or if z equal to fxy, then dz by dx and dz by dy. So if this is x-axis and this is y-axis, this is z-axis, then if I make a cross section in xz, so if this is xz plane and this is yz plane, in the xz plane, whatever the curve we are seeing as a 2D, there dz by dx, and then in yz plane, dz by dy. These are called partial derivatives. These are called partial derivatives. Now idea is that if we see closely, then partial derivatives are nothing but directional derivative only. Partial derivatives are nothing but directional derivative only. Okay. So dz by dx, dz by dx is partial derivative of function f, or df by dx is partial derivative of function f along okay, along direction, I would say directional derivative. So dz by dx is directional derivative of f along vector, unit vector I. Dz by dy is directional derivative of fxy, graph function fxy, along unit vector j. So the partial derivatives are nothing but directional derivative along I-axis, j-axis and k-axis. So now what we get through the partial derivative? Through partial derivative, we see that along x-axis at any point x, along x-axis at any point x, if I make changes of 1 unit, if I make changes of 1 unit, then I have 2 points on x. One point x1, another point x2. Distance between them is 1. This is x1 is nothing but x. At any point x, if I go 1 unit along right direction, so I call this is x2y2 or x2, and this is x1 y1, or anyway it is x. Now if I have z at one and z at another, if I subtract the two z, then that is called delta z. Delta z per unit change along x-axis brings how much? So per unit change, not one, no, not one in x, per unit can be anything. It can be nanometer also. So dz by dx is nothing but directional derivative of z along x-axis. Similar way, y I can do. Now question arises is, if this is x-axis, this is y-axis, these are unit vector, then suppose this is the origin, then there is another direction I can think. X-axis, y-axis, then there is another direction axis I can think. That is nothing but u vector, I vector, j vector, u vector. Now on the u vector I have a point called u. U can be any xy. If I have a point on u, now at this point I have z value. Now I go one unit along the u vector and then I get another z value. What is delta z by delta u? Straightforward. This is directional derivative of graph function f along the vector u. dz delta z by delta u. dz by du. Okay, along any vector u, at any point u, if there is one unit of change in u direction, then how many unit of change at these 2 points along the z direction? Delta z by delta u. Now, in the previous session, in the first session, what we saw that dz by, now delta z by delta u, if delta u tends to 0, then it becomes dz by du. By definition, what is delta z by delta u is f function at u plus delta u. So if I have a point u, if u is a vector at any point, it is u, then if I move delta u along the u, then I have 2 points. One point u, another is u plus delta u. What is z value at u plus delta u and what is z value at u? Those two z value if I subtract, then it becomes delta z by delta u. So function value fxy, function value at u plus delta u minus function value at u divided by delta u gives delta z by delta u. Now then we saw that if I go for kind of polynomial approximation of fxy, that is gxy, if gxy is polynomial approximation of gxy is whatever it is, sorry, fxy is whatever it is, if I can represent it using polynomial equation. So polynomial equation of order 1 is also called local linearity. Local linearity in the sense, if I have a sphere and then I keep go near the sphere, near, then at one point I'll start seeing a tangent surface, flat surface, not the round, the way I am sitting on the earth. So if someone see earth from the moon, then he will see it is completely a sphere. But if he talks to me and he says that how you are enjoying a sphere, then I said, you are you mad? Means I am sitting on a flat surface here. I don't know what you are talking about. Then he would say, I am seeing from here, it is a sphere, but you are saying you are sitting on a flat surface. I would say, I can see you that you are sitting on a sphere, but I am sitting on a flat surface. Person sitting on moon would say, I am sitting on a flat surface, you are sitting on a sphere. Means if someone from moon, if he keep coming near earth, at one moment he will see the complete earth, but if we go down, if we descend further, one point will come, he will start seeing earth as a flat surface. That is called local linearity. Local linearity is nothing but polynomial approximation of a function in the first order. So if fxy is a function and gxy is a local linearity of the function or polynomial equation approximation of fxy, where order is 1, then gxy equal to fx means dz by dx, fx into x plus fy into y. So z equal to fx into x plus fy into y. Now we saw that that is nothing but if I have a surface and dz by dx is negative along x-axis and it is positive along y-axis, then from origin, whatever x we go, that x into dz by dx gives me a vertical, and then in y direction, wherever y I am, into the dz by d give me the z direction. Both z we add, that z is actually the z value at x comma y. So that is z equal to dz by dx into x plus dz by dy into y. Now from y, if I take any delta distance delta x comma y, from there I go in x direction delta x and y direction delta y. Then for that whatever new point I have, for there I have a z. What is delta z? So if I differentiate it here, if z equal to fx delta x plus fy, I mean z equal to fx x plus fyy, then delta z equal to fx delta x plus fx delta y. Delta z equal to dz by dx into delta x plus dz by dy into delta y. This is what we saw. If that is the case, then delta z we have got. Now, if we go the actual differential equation, that is delta z by delta u, that is dz by du, equal to f at u plus delta u minus f at u divided by delta u. So, numerator is delta z only. Now, numerator I can substitute with fx delta x plus fy delta y divided by delta u. So delta x is nothing but the x component of the delta u, and delta y is x component of the delta delta u. So I can say now fx delta u ux plus fy into delta uy divided by delta u. So this is what is the result that we got. Now I have fxy equal to x square plus y square, that is paraboloid. X square plus y square, that is a paraboloid. If that is a paraboloid, then what is the kind of df by du or dz by du, directional derivative of graph function x square plus y square along u vector, where u vector is I plus j at point 1 comma 0. So that is the question. If I have a function fxy equal to x square plus y square, then what is directional derivative of function f along vector u? Directional derivative of vector function f along vector u, okay, when the vector u is I plus j and at point 1 comma 0, means on x axis 1 comma 0, if u vector if u vector is if u vector is okay, so when u vector is I plus j, then what is df by dz? I mean df by du or dfxy by du or dz by du, where fxy is x square plus y square. Now we saw that delta z, delta is fx into delta x plus fy into delta y divided by delta u. So now fx x square plus y square, fx is dz by dx, fx is 2x. Delta x is x component of the delta u. So if delta u I have taken, then x component of the delta u I have to take, plus fy. Fy is again 2y into uxy divided by delta u. Now what is u? Now u vector is I plus j. First we have to calculate the unit vector. So that is nothing but I plus j divided by square root of 2, that is a unit vector. So the x component of the unit vector is 1 by root 2. Y component of the unit vector is 1 by root 2. So if 1 is the length, unit vector is means length is 1. If 1 is the length, then x component is 1 by square root of 2. If 1 is the length, then y component is 1 by square root of 2. If delta u is the length, then x component is delta u into 1 by square root of 2. Delta u into 1 by square root of 2, that is y component. So 2x, fx is 2x, 2x into delta u by square root of 2 plus f2y into delta u by square root of 2 divided by delta u. So delta u would go away. Now 2y. So x and y is at 1 comma 0. This is what we want. So 1 comma 0 means y component is 0. So it remains as 2x 2x divided by square root, that's it, of 2. So x is 1, so 2 by square root of 2 comes as a square root of 2. So the directional derivative of function f along vector u, where u is 1 plus j and fxy is x square plus y square at point 1 comma 0, is square root of 2. This is what we calculated. Now idea is, can we try doing this by traditional differentiation method? Traditional differentiation is delta z by delta u. Delta z is function at u plus delta u minus function value at u divided by delta u. Okay. Now let's consider that I have x-axis and y-axis and u vector. Okay, so this is x-axis, this is y-axis, and this is u vector. Y-axis, x-axis, u vector, y-axis, u vector. U vector, now idea is that we are at 1 comma 0. If this is x-axis, then this is 1 comma 0. If this is 1 comma 0, then u is a vector. U is not a line. U equal to I plus j. U equal to I plus j. If this is x-axis and this is 1 comma 0, then u vector has a direction, only direction and magnitude. I plus j, if I say, then it is at 45 degree from x-axis. There is a array, there is a vector. So if this is 1 comma 0, if it is origin, then it is exactly 45 degree. This is x-axis 45 degree and then y-axis. Now at 1 comma 0, from here I will have another vector from here that will cut it. Okay, so from here, if it is 1 comma 0, then from here I have another line that is 45 degree, from here. This is I plus j. Okay, this is I plus j. This is y-axis. This is x-axis. This is 45 degree, and this point, the junction point, is 1 comma 0. If that is true, then we are talking about this direction, that is I plus j. U vector is vector, it's not a line. So vector has only direction and magnitude. You can shift here and there. If you want a vector to represent as a line, then you have to think about parameterization in the vector. Right now it is R vector, but you have to talk about RT, parameterization of the R vector. That will give you exact vector as a line, where it will have offset here and there. Otherwise, it has only the direction. So, directional derivative of function fxy along vector u at point 1 comma 0, where vector u is I plus j and fxy is x square plus y square. That is the concept. Now consider 1 comma 0 point, from 1 comma 0 point, from 1 comma 0, 1 comma 0 point, it is origin 1 comma 0 point on x axis. I have I plus j as the vector at 45. Now if I move along 1, then the position that will be 1. If I move 1 along x-axis and 1 along y-axis on this line, means if I move square root of 2, if I move a square root of 2 along this, okay, then what would be the, I am taking it simplicity. So the point what I am taking here is, if it is I plus j, if I move 1 along x-axis and if I move 1 along y-axis, then next point would be 2 comma 1. If it is 1 dot 0, these examples are not available anywhere else. So it is our example. So 1 comma 0 is 1 point, and next point on the u vector is 2 comma 1. Now we will use traditional way to calculate the dz by dx. What is dz? So z at 2 comma 1, z at 1 comma 0 divided by its length. Now, now z at 2 comma 1 is x square plus y square. That is square root of, that is 5. 2 comma 1 x square plus y square is 5. Z at 1 comma 0 is 1, that is 4. 4 divided by 1 square, that is the distance I have taken, 1 square plus 1 square, square root. So 4 by square root of 2. That will come as 2 square root of 2. But actual answer is square root of 2, not 2 into square root of 2. Where is the problem? Problem is the distance we have taken is 1 square root of 2. That is very big difference for differentiation. Delta z by delta u means delta u tends to 0. Then only we can say at a particular point what is the, at every point dz by du would change. So dz by du is proportional, is dependent upon the independent variable. So delta u should be infinitesimally small. Let's take now in x direction I move 0.1, in y direction I move 0.1, not 1 1. Then now I have x square plus y square. So now x is 1.1 and y is 0.1. So 1.1 x square is 1.21. 11 into 11 will come in India. We can do things through our own way. So it will come 121. So 120, 11 into 11, we can calculate in one go only. No, we don't need any calculator or something like that. So 11 into 11 is 121, that is 1.21. So it is 1.21 plus y square is 0.01. So that will come as 1.22 minus x square plus y square at 1 comma 0. So there are 2 points now. One is 1.1 comma 0.1 and another is 1 comma 0. So there it will come as 1. So 1.22 minus 1 will come as 0.22. So 0.22 is numerator, whereas denominator is a square of 0.1 plus a square of 0.1 square root. That will come as a square root of 0.02. That will come as 0.0144. Means a square root of 2 multiplied by 0.01. Point 0.02. Okay, point 0.1 into 0.1. 0.1 square is 0.01 plus 0.01 square root. Then it will be 0.02 square root. It will come as, it will come as 1.44. A square root of 2 multiplied by, divide by 10 and multiplied by 0.1. That will come as 0.144. Okay, so it will come as 0.144. Now the numerator is 0.22 by 0.14. That is nothing but 2.2 divided by square root of 2. So square root of 2 is 1.44. It is near to 1.5. So 2.2 divided by 1.55. So it will come around, more or less around 1.7, I believe. I don't know. I have never used calculator here. So 1.7. But actual answer is the square root of 2, that is 1.44. So 1.44 and 1.7 is nearer than 2 into square root of 2. So when delta u we are taking smaller, we will tend to come to the value dz by du, where u vector is I plus j, and then z equal to x square plus y square at 1 comma 0 is nothing but near to a square root of 2 if I calculate through the traditional differentiation way, that is function at u plus delta u minus function value at u divided by delta u. So we saw in real life that if delta u is big, their answer is more error prone. If we bring it near, then it will come to the real differentiation. So real differentiation is through algebra always. This is what I always say, that trust on the algebra, not on the kind of approximation here. Why it is required? When you have algebraic function, then no need to go for approximation here and there. So now it is square root of 2. This is what we saw. Now next question arises. Next question that is arising here is that what we are trying to achieve and how it is. So first of all, dz by du we calculated through two different ways. One is through traditional differentiation and another one is through polynomial approximation through algebraic way. Now through algebraic way, what we saw, dz by du is nothing but dot product of gradient vector of f and unit vector of u. This is what we saw. If I have u vector and if I have gradient vector of f, if I do dot product of them, that gives me dz by du. That is the scenario. Now, suppose that this is x-axis and this is y-axis. This is x-axis and this is y-axis. Now, this is u vector. If u vector has theta degree here, then what is dz by du? Certainly, it is dot product of dot. Now we are talking about gradient vector. If gradient vector x for x square plus y square is 2xi plus 2yj, that is the gradient vector. If that is the gradient vector, then gradient vector at 1 comma 0 where y-axis is 0 is 2i. 2xi plus 2yj is 2i. If it is 2i, 2i is the net gradient vector, then it is along the x-axis. And this is our unit vector u. If unit vector is along the x-axis, then dot product means cos theta between them and their magnitude. So the magnitude of u vector, okay, whatever it is, if I don't take unit vector, then whatever it is and whatever the magnitude of the vector gradient vector we are taking into cos theta, angle between them. If angle between them is 0, if they are along, so if gradient vector is along x-axis and this is u vector and they are along with it, then the maximum dz by du I can see. Means whatever the maximum dz by du I can see when the gradient vector is x-axis and u is also x-axis. Then dz by du maximum we will see it is nothing but dz by dx only. If maximum we are seeing and if I take u as unit vector, then it will come dz by du equal to dz by dx into delta x or ux delta ux plus dz by dy into delta uy. This is what we saw. Now the kind of dz by dy or uy, that component is missing somehow. When means dz by dy is 2y at point y equal to 0, means that factor is missing now. Dz by dx is 2x into ux. Okay, so dz by dx is the partial derivative along x-axis. Ux is the x component. So it is direct multiplication. If I take ux as 0, as 1, then it is exactly dz by dx. Means what we are trying to say, that if u vector is along x-axis, then dz by du is nothing but dz by dx. Now if u is moving at angle theta, now if it is making angle theta, then if x-axis is the gradient vector, because we are taking gradient vector 2xi plus 2yj at point 1 comma 0, then gradient vector is 2i. Then u is making theta degree with the x-axis, then dz by du is gradient vector, that is 2i dot product of the I plus j or u vector. Now we will get only the I component or whatever. If I see the dot product, then magnitude of the gradient vector into cos theta. Now their magnitude cannot be multiplied directly because they will have cos theta, and cos theta is less than equal to 1. So dz by du is maximum when it is along the gradient vector, and then it starts decreasing if it is making angle with the gradient vector. When it is at 90 degree, this u from the gradient vector, then magnitude of gradient vector into magnitude of u into cos theta. So cos 90 is 0. So dz by du when u is along y-axis and gradient vector is along x-axis is 0. There is no variation. There is no variation we see in the function fxy. No rate of change we see in function fxy along a vector that is 90 degree from the gradient vector. So if gradient vector is along x-axis and u vector is along y-axis, and then we try to calculate dz by du, then there is no dz by du. It is 0. Let's see more on it. dz by du is nothing but function value at u plus delta u minus function value at u divided by delta u. U plus delta u is nothing but function value at x plus delta x, means delta x means delta ux plus comma y plus delta uy, whatever is the function value f at x plus delta ux comma y plus delta uy minus fxy divided by delta u. Okay. Now if we see closely here in this case, now x is 1 and y is 0. We are doing all the calculation at point 1 comma 0. So fx plus delta ux plus y is 0. F, so function value at f, x is x plus delta ux comma y is 0. So delta y. Okay, delta y. Now what I'm trying to calculate here is that let's consider that our gradient vector is along x-axis and u is along y-axis. Okay, if that is the case, then at 1.0, now the u vector is along y-axis, and anyway our gradient is along the x-axis. I mean, this is the scenario. But anyway, now what I am trying to do is dz by dx. Now leave the gradient vector because we are calculating through traditional way. dz by du. dz by du when z equal to x square plus y square and u equal to j, not I plus j. Unit vector is u vector is along y-axis, u equal to j, and fxy equal to x square plus y square. What is dz by du or dfxy by du at point 1 comma 0? If that is the case, then I have to take one more point, and that will be a delta u along the u vector from 1 comma 0, and then I have to subtract the z value divided by delta u. So at the next point, what we are seeing along y-axis is x plus delta x. So there is no delta x because we are moving along the y-axis one. So there is no delta x now. So fx comma y plus delta y. So there is no y because y is 0. So fx is 1. So f at 1 comma delta y minus then f at 1 because y is 0. So f at x plus delta x comma y plus delta y minus fxy divided by delta u. X is 1, delta x is 0, y is 0, delta y is there. So, or I can say fx comma fx comma y plus delta y. If I don't take xy value, just leave it that I don't take xy value as 1 comma 0. Okay, now let's see the scenario, then we'll take the value. Now we are moving in y direction. because our u vector is j, not I plus j. F x plus delta x comma y plus delta y. Delta x is not there because we are moving in y direction. So f x comma y plus delta y minus fxy divided by delta u. This is nothing but delta u is nothing but delta y because we are moving in y direction. This is nothing but exact dz by du. Can you see this? dz by dy, dz by dy is nothing but fx comma y plus delta y minus fxy divided by delta y. dz by dx is nothing but fx plus delta x comma y minus fxy divided by delta x. dz by dy is fx comma y plus delta y minus fxy divided by delta y. Now, if I have a point 1 comma 0, from there I am moving in y direction. That is the u is j. If that is the case, then delta z by delta u, dz by du is nothing but f function at u plus delta u minus function at u divided by delta u. If I am moving delta u in the u direction, but delta u is nothing but delta y because there is no delta x. Delta u is delta x plus square plus delta y square root. Delta x is not there because we are moving in y direction. So if that is the case, then function value at u plus delta u is x plus delta x. So delta x is not there. So fx comma y plus delta y minus fxy divided by delta y, that is dz by dy. So this is what I am trying to say, that dz by dy, dz by dx both are orthogonal to each other. dz by dx is in x along, that vector is along I direction. dz by dy is a vector along j direction. If I do dot product of I and j, it would result in 0. So dz by du, dz by du, when angle between u and x axis, dz by du, when the gradient dz by du is nothing but gradient vector of z or f dot product with u. So if gradient vector of f is along x axis, that we are seeing at point 1 comma 0. So if gradient vector is along x axis, and then u vector is I, not I plus j. So u vector is also along x axis. This is nothing but dz by du equal to dz by dx. That is nothing but the dot product, means whatever the magnitude of gradient vector of f into magnitude of unit of vector u into cos theta. So when they are along same angle, then theta is 0. If theta is 0, then dz by du, when gradient vector is along x axis, is nothing, and gradient vector is along x axis and u vector is also along x axis, then dz by du is nothing but dz by dx. Or if gradient vector is not along x-axis, gradient vector is anywhere. If gradient vector is anywhere, still if u vector coincide with the gradient vector, if u vector coincide with the gradient vector, then when angle is 0, then dz by du is nothing but gradient vector itself, because cos theta is 0, and if you take unit vector, then the strength of the u is 1 1. So the value of dz by du is gradient vector itself, magnitude of gradient vector itself, if u vector is along the gradient vector. If u vector is making angle from the gradient vector, then it will be I have to multiply the cos theta as per the dot product. If it becomes perpendicular to it, then gradient to gradient vector, then dz by du is 0. Means there is, if I make unit variation along u vector, and I try to see how much the function has changed, where when the gradient at point 1 comma 0, I can take any point on the gradient vector when u vector is perpendicular to the gradient vector. If I take any x comma y, x comma y that falls on gradient vector, and I am trying to calculate dz by du at x comma y when u is perpendicular to the gradient vector, then it will result in 0. Gradient vector and vector u, these are vectors. So vector u, if it is from origin, it is here, but it will be anywhere I can take, because vector has no position or something like that. So now we learned that dz by du is nothing but dot product of gradient vector and unit vector u. So practically we saw it's a kind of rotating guide. Gradient u vector is a if I keep rotating around along the gradient vector, then at one point it will be exactly as gradient vector. It would keep decreasing dz by du. It will become 0. It will become minimum here because it is in opposite direction, and then 0 again at 270 degree, and then same as 360 or 0 degree. So this is what we saw. Okay, so what is the next? Now we calculated dz by du or delta z by delta u. dz by du is delta z by delta u. Delta z is f at u plus delta u minus f at u divided by delta u, or fx into delta ux plus fy into delta uy. We calculated with when the x was 1, delta ux was 1, delta uy was 1, and later we saw it gives high error. Then we turned up delta x and delta y as 0.1, 0.1. It came to near result. What about if I see this equation delta z by delta u, then this is polynomial approximation of order 1, that is fx delta x plus fy delta y. What about higher order? So that will result in fx delta x plus fy delta y plus fxx delta x whole square divided by factorial of 2 plus fxy delta x delta y by factorial of 1 1 plus fyy delta y whole square divided by factorial of 2. So the polynomial, if I go beyond, I can go in power of 3, 4, 5, 6 up to n. So polynomial approximation of function fxy as gxy as far as dual order or multiple order is concerned, that is fx into delta ux plus fy into delta uy plus fxx into delta ux whole square divided by factorial of 2 plus fxy delta ux delta uy plus fyy delta uy square by factorial of 2. Now, if this is the case, now let's calculate the delta z again at 1.0, where u vector is I plus j and fxy is x square plus y square. Now I calculated fx delta ux plus fy delta uy as square root of 2. Now fxx for x square plus y square equation is 2. Now fxx is 2. Delta ux is 1 by square root of 2. Delta ux is delta u into 1 by square root of 2. So delta u by square root of 2 whole square plus fxy is 0 and fyy is 0 because we are taking at 1 comma 0. So it results in fx delta ux plus fxx delta ux whole square by delta u whole square by factorial of 2. This is what we are seeing. Now fx, if I take fx, then it is 2. 2 into delta ux. Delta ux is of, if I take for unit vector, if I use delta uy, just forget it, then dz by dz by delta z equal to fx x plus fyy plus fx x square by factorial of 2 plus fxy x into y plus fyy square by factorial of 2. Delta z, not z, delta z equal to fx delta x plus fy delta y plus fxx delta x square by factorial of 2 plus fxy x into y plus fyy delta y is whole square by factorial of 2. Now, fy and fxy and fyy all are 0 at point 1 comma 0. Now delta z equal to fx into delta x, that is delta x is the x component of the unit vector u plus fxx delta x whole square by factorial of 2. So fx at 1 comma 0 is 2x, means 2. 2 into 1 by square root of 2, that is square root of 2, plus fxx is 2 into 1 by square root of 2 whole square. So 2 into 1 by 2, that is 1 by factorial of 2. So 1 by 2, that is 0.5. So actual delta z, if we see, then actual delta z is 1. Actual the delta z, what we are seeing is not through the polynomial kind of substitution, then it is not the kind of delta z what we are getting. So dz by du. So I will reiterate what I have said. So delta z equal to fx delta ux plus fxx delta ux whole square by factorial 2. Other fy and fxy and fyy at point 1 comma 0 I am removing. So delta z by delta u, dz by du we are calculating. That will come as fx delta ux plus fxx delta ux whole square by factorial of 2 whole divided by delta u. The delta ux is nothing but delta ux. If we calculate, then it is nothing but delta u into the x component of the factor of the unit vector. So delta u into 1 by delta u into 1 by square root of 2. So delta u we cancel it. Approximately it would come like this. Now fxx plus x square. So x square so is kind of delta u whole square into 1 by square root of 2 whole square. So more or less we are seeing like this. Now it will come as fx delta u will go away, fx into 1 by square root of 2 plus fxx delta u whole square into 1 by square root of 2 whole square divided by factorial of 2, then divided by square, then delta u and delta u whole square will cut out and it will result in fxx into delta u into 1 by square root of 2 whole square by factorial of 2. So first is fx into 1 by square root of 2. So fx is 2x at 1.0, it is 2. 2 by square root of 2, that will come as square root of 2. Square root of 2 plus fxx. fxx is 2. 2 into delta u into 1 by square root of 2 whole square, that is 1 by 2. 2 by 2 is 2 into 1 by 2 is 1. So it will result in delta u divided by factorial of 2. So delta u, if it is tends to 0, then this factor is 0, 1. So net we see, if I take the polynomial equation in quadratic function also, then it results in a square root of 2. I cannot take power fxxx because it will result in triple differentiation in 0, 1. Anyway, now we have found that dz by dx, if I want to calculate, then it is actually gradient vector of f dot product with unit vector of u. Because if I take higher degree in the polynomial expression of polynomial approximation gxy of the fxy, then delta u remains in the numerator, because if I do delta ux whole square, that is delta u whole square into 1 by square root of 2, because if u is I plus j, then unit vector is I plus j divided by square root of 2. So x component is 1 by square root of 2, y component is 1 by square root of 2. If unit vector is one distance, then x component is 1 by square root of 2. Then if unit vector is delta u distance, it is delta u by square root of 2. So delta ux is nothing but delta u by square root of 2. So fx into delta ux plus fxx into delta ux whole square divided by factorial of 2. So fx into 2 divided by delta of u, because we are calculating delta z by delta u, dz by du. Delta z is fx into delta ux plus fxx delta ux whole square by factorial of 2. Now full divided by delta u, dz by du. Now first is delta ux is delta u by factorial of 2. So delta u cut off, then it becomes fx into a 1 by a square root of 2. Next is fxx into delta u whole square into 1 by square root of 2 whole square divided by factorial of 2 full divided by delta u. So it comes in term of delta u, where delta u tends to 0, then second order is 0. So net result is 2x, that is fx at 1 comma 0 2 by square root of 2 1. So with the polynomial these are not available anywhere in the book. So we tried polynomial approximation with the order 1, that is called local linearity, and with the power of 2. 3 we cannot go, because x square plus y square 3 partial differentiation anyway it would result in 0. Anyway, so now I can say with confidence that dz by du is nothing but gradient vector of z or f dot product with unit vector of u. This is what we saw. So these are theory. What is the practical use of the directional derivative along any vector? Immense use, not use, immense use. This is what I say, that don't hire any MBA guy or something like that. As far as the actual management is concerned, hire a mathematician, because mathematician would bind everything in a formula. That formula will have independent variable in time, in all the variable thing you saw while the production and when you sell in the market. Depending upon the scenario, keep changing the independent variable, and then see the maximization in the minimization in the investment, buying the raw material where things would minimize to get the maximum production, and then sell it. So the cost to the company should be minimum, and when you sell, the net profit, the kind of revenue should be maximum, net profit should be maximum. Only thing that lacks is the exact algebraic equation that we get, and then we have maximization values or minimization value as far as independent components value is concerned. So that we will see in practical sense what is directional derivative along any vector u makes sense when industry comes into the picture. Profitability, how it is so genius in profitability. So Lagrange way and those things we replace now with the gradient vector, with the directional derivative along vector u. This whatever we will talk now, this is pure research way, and it is not available anywhere else. It is only with us, and we will file patent for it. This is what we have thought. So let's move.